Great. Yeah, so I'm the Education Content Manager for this year's CodeDay Labs. I'm happy to welcome Michael Kalish, and he will be talking to us today about containerized software development. And Michael, if you'd like to give a short introduction about yourself, and then we can get going.
Alrighty, yep. Yeah, so my name is Michael Kalish. And yeah, so we're going to be talking about an introduction to containerized software today. We're going to be sort of exploring the history of virtualization, trying to examine where we came from to see where we ended up today, with Docker being sort of one of the big buzzwords that maybe some of you heard of. But that technology that's so popular today is built upon 60 years of, or 65 years of work on virtualization technology that sort of spans sort of how computers came to be. But more on myself. Oops, sorry, hold on, give me 1 second. All right, pardon, I might have to reshare my screen. Sorry about that. But yeah, so like I've said, my name is Michael Kalish. I've been a software developer for, I guess, to update this slide, now 9 years. Over my time, I've gotten a chance to work with a ton of great companies. I've done education, I've done insurance, really had a chance to do a lot of stuff. I've done sort of civic work. Currently, today, I am a lead engineer at a company called Curiosity Media. If you haven't heard of that, you might have heard of some of our products. We're the team behind Spanish Dict and Fluencia, and now newly Ingles.com. So we are one of the most comprehensive Spanish to English and English to Spanish dictionaries on the web, as well as a great sort of tool for learning Spanish. About my personal life, yeah, so I have a dog. He's the picture on the left here. He's much bigger than that now. And that and traveling are sort of my two biggest hobbies. And then the picture on the right is my wife and I were in Japan 2 years ago. And this is at a sort of cool exhibit. So when I'm not coding, I try either walking the dog or trying to travel. So enough about me. So if we go and talk about the agenda, what are we going to talk about today? So where we are today, we're going to sort of start there. We are then going to go way back in time, relatively speaking for computers, to sort of talk about where computers came, and then try to walk up through time to talk about where virtualization started, what were some of the first attempts, and then sort of trying to get to the root of why did Docker become so popular and what problem were containers really solving for the community. And then feel free to ask questions in the chat. I'll check that periodically, or raise your hand. I'll also leave some time at the end for any other questions, but definitely feel free to interrupt me if you have anything you'd like to ask, or would like me to pause and revisit slides. All right, so where we are today. So I found this neat word map of all the various software languages that people are currently using. It's the bigger the word, the more use we see in the community. But as you sort of just wrap your head around this, there's a lot here. There's a lot of languages, there's a lot of tools. Some of them work similarly, some of them work nothing like each other. Some of them run only on Mac, some of them only run on Windows. It's a little bit of a mess, and it's sort of daunting as a software developer. At the same time, it's great because if you look at this map, there are enough stuff to learn here for any lifetime, which is great. So you can constantly learn new stuff, new languages. But one of the downsides is that because there are so many languages and so much to learn, the number of tools and applications, compilers, operating systems has sort of exploded. So like I said, this only captures sort of software development languages, doesn't even begin to capture the various different compilers and operating systems like Windows, Macs, and Linux. And so this also leads to the problem where, I, as a software developer, I'm working on my computer, it's going great. I'm going to launch this killer new feature. I can't wait. And then I click deploy, it sends it out to the web. All of a sudden it doesn't work anymore. My quality assurance team member is coming back to me and he says, you told me this thing worked, it worked great. And all I can say to him is, well, it worked on my machine. And, that makes me feel good, but realistically doesn't make our users and our stakeholders happy because it's not working in live. And so this is something that developers sort of frequently are running into, where the work they're doing is happening on their personal computers in sort of a very sanitized environment. And then they're moving this to either the cloud or physical machines where that environment is going to be different. And so it might not run the same way. You might get subtle issues that are often hard to debug because, like I said, it worked on my machine, and now I have to figure out why it's not working on this other machine. And so this is sort of where we are today, and in many ways is one of the problems that Docker was sort of aiming to tackle and fix. So that's where we are. So let's wind back the clock and go back all the way back to sort of when computers were first starting. So when computers were sort of becoming a thing, this is pre-1963, the main player in town was a company you might have heard of called IBM. They were the original makers of sort of the original computer as we sort of begin to understand it. Think huge rooms with those floor-to-ceiling computers and people walking in and plugging stuff in. And realistically, they were the only commercial vendors for computers. You could come in and say, hello, IBM, I have this data I need to crunch, I need to analyze it. I would like to rent one of your computers for 2 hours. You go in, you would enter your program into the computer, you would press play, and then you go on the other side and it would print out some results. It worked great. It was a really good system. It was simple. But as you can sort of imagine, the downside is that, it takes a long time to write those programs. And since these machines only flow in one way, there's no interaction. And more importantly, they can only do one thing at a time. So you have these giant, huge machines that people need to take time slices of. So I go in and rent, I'm done, I hand it off to the next person. That is super tedious, and it worked before computers were really a big deal. Think that this is 1963. No one even had the idea that you would be typing or moving a mouse. Worked great for companies trying to crunch data. But as we can see now, sort of looking back, there's a lot of downsides to only being able to run one program and not have any sort of interruption here. And then for those who are curious, this picture that I have on the screen is sort of a very, very simplistic diagram of how some of these original computers worked. So we'd starting from left to right, someone would write their program, which are these sort of nodes A, C, B, and H. Someone would insert some data on the start side and the program would execute. And so you would go to A, maybe to B a couple times, back to A, C. Finally, you would have the answer, H would split it out. So this is sort of how computers worked and sort of when we were originally talking here. All right, 1963. So what happens in 1963? This is the Beatles actually released their very first single in the USA, Please Please Me. And so the Beatles are sort of, Beatlemania is striking the US. Also in 1963, DARPA, this might be another acronym you've heard, but the Defense Advanced Research Project Agency gives MIT a grant. So DARPA, for those who might not know, is sort of the, yes, so in the comments, DFA and NFA machines, yes. And so, yes, those are sort of, talking about computer architecture. Other terms people might be familiar with are Turing machines. All right, so DARPA. So DARPA, probably more famously known as sort of the organization that sort of spurred the development of the internet. So there's this idea of DARPANet. This is a little later, but that's how I think DARPA is probably sort of more famously known as. But they also played a critical role in virtualization here. So DARPA went on and said to MIT, here's $2 million, 1963 money, that's actually comes out to 16 million today's money. We want you to do research into operating systems, artificial intelligence, computational theory, sort of like low-level computer architecture. MIT was like, great, let's do it. But the existing computers don't really work for what we want to do. We want to be able to run experiments fast. We don't want to be constantly waiting for this sort of last screen where I put in program and I wait a while to figure it out. I want to be able to do multiple things at once. So MIT takes this grant and then goes out and puts a bid out to a bunch of people, including IBM and GE and some other vendors, to build sort of a new set of computers capable of running more than one program at once with user interaction. And so if we think back to those couple slides here, that is very different from this architecture we have up on the screen. There's no room for human interaction to pause and do something else, and you have to wait, and only one program can run at a time. So this was sort of a, a brand new idea. It seems really simple today, but yeah, so MIT went out to all these people, like I said, IBM, GE, and they said, build it. And so of course, the bid goes to GE. So I'm sure some of you, that might be a little shocking. I did just say that not too long ago that IBM was the really only player in the town and sort of invented the computer. So why did IBM not have any interest in taking this bid from MIT to build this computer? From IBM's perspective, big company, they had a system that worked. People were paying for it. And why do you need to change it? And from IBM's perspective, and now once again, we have the hindsight's 2020, they thought it wasn't going to be commercially viable. They were, they viewed computers as a way of only taking some data, processing out and returning results. It really didn't have it in their head that we were going to create sort of these really interactive devices. So GE takes the money, IBM says no, and they're sort of off to the races. Let's fast forward another 5 years, 1968. This is actually the same year that Apollo 8 launches and humans orbit the moon for the first time. And so, which I hope this sort of puts into light how impressive that feat was, considering the kinds of computers that the astronauts were working with in order to accomplish this feat. So what else was happening in 1968? So, well, GE wins the bid because IBM didn't even bother, and then immediately had success. This serves as a big wake-up call to IBM that they missed something really important when MIT asked for bids to build these computers. And so they immediately turn around and start working on building a new type of computer architecture here. So the first version, or the first one they make available sort of internally within IBM, is available in 1968, and then it's another 4 years before they make it commercially available. So this diagram that we're looking at is a really sort of another simple sort of distilled version of how these systems worked. And so when we're talking about computers, computer hardware, we're talking about CPUs, we're talking about RAM, we're talking about hard drives. And so in those old designs of computers that were very linear, the one program using it used all of it, and only one program could use those resources. So these smart people at IBM and GE and MIT realized that, well, that's sort of wasteful. Programs can share these resources and make better use of them and more efficiently. So this is a simple diagram sort of showing how this would have worked. So if you can imagine these users as being either people or programs running or sensors, like satellite sensors, they can be anything. But the idea is that internally, there's still one CPU, there's still only a tiny set of memory, but we're able to share these resources among a bunch of these processes. And so, and in some ways, this was actually sort of similar to what IBM was doing, except for it happened so slowly. I got it from 12 to 2, and then my fellow company got it from 2 to 4. We were technically sharing those resources already. But what they sort of discovered was that the computers are fast enough can share them so fast that from a human user perspective, it appears that they're all happening simultaneously. So even though our computers continue to be sort of linear, when we're doing multiple things on the computer, assuming we only have a single processor, what is actually happening under the hood is every program and user interaction is taking a turn using the hardware. Cool. So I just want to pause there real quick because there's a lot of sort of boring, not boring, but black and white diagrams. If there were any questions or comments, or if anyone wanted to see any slides, it's like 10 seconds. Cool. All right. So IBM starts to have some immediate success. Everyone realizes, oh, it's really great if computers can run multiple programs and that humans can interact with the programs as they are running. And this ultimately leads to something that I assume a lot of people are also familiar with. It leads to Unix in 1972. So, all right, so where we came from, we're talking about, all right, we have physical hardware, there's a real CPU, there's RAM and memory. That's great. That's sort of easy to imagine sharing. Where Unix sort of took this the next step is, all right, so if we can share hardware, why can't we share virtual things like folders and documents? And so the idea was that this was virtualization at the user level. So even though under the hood Unix, there's just one giant file system, I, as a user, have my sort of space of that file system. I'm sharing with a bunch of people. But similarly, as to this slide, where I was sharing hardware and CPU and I didn't even know it, in Unix, the user is sharing a folder system, even though they aren't aware of that fact either. So this was sort of, we were talking, so the previous iterations, we are virtualizing around hardware. And then Unix sort of takes this next step and allows us to virtualize around sort of the virtualization around the user, sort of the concept of a user within a system. All right. So that's sort of the state of things for a while in development. I mean, in between 1972 and 94, a lot of these ideas are continued to be built on. We see, Mac, Windows are sort of come up. I forget which version of Windows, but at least, we're about to have 94, we're about to have Windows 95. So computers have, in many ways, sort of hit mainstream. The internet is becoming a thing. But 1994 was the 1.0 release of Linux. So this was sort of a, for those that don't know, Linux is an open source operating system built on top of the Unix that we mentioned here. And it was sort of the next step or the next sort of iteration of this process of Unix. And for a long time, almost all web software that was used, or even software, was run on Linux. All right, so let's talk about what else was happening in 1994. So this is a little comic that I like from a webcomic called XKCD. I'm sure some of you are familiar with it. So the idea is that these developers are sort of goofing around at work, and their boss yells at them, and they tell them that the code is compiling, and the boss understands that and says, "Okay, you can keep playing with swords." Pretty funny, in some ways, sort of true at the time. So, which is true at the time. So, going back to what we talked about, so we're talking about how we're figuring out how to share all these sort of physical resources and virtualize these resources. We figured out how to share sort of user space and share folders and documents. But still, at the end of the day, the problem with our sort of software that we were writing was that each piece of software, when we actually went to run it on Linux or Windows, different versions of Linux or Mac, that software that was going to run on those individual operating systems needed to be essentially custom made. And so now individual developers weren't individually writing software. And that's sort of where we got this idea for compiling. So a software would write some code, a developer would write some code. They would compile it to a version that would run on Windows. They would compile it to a version that runs on Mac. They would compile it to a version that runs on various different versions of Linux. So that's great, but software is still not very portable. And we're sort of missing that sort of virtualization on the software layer level. Every program is in some ways bespoke for the operating system it runs on. We get weird situations where maybe one operating system, the software works just as we expected, but another one, because of slight differences in implementation, software doesn't work. So a new company comes around called Sun, and they go, I think we can do this better. And they invented something called the Java Virtual Machine, or the JVM. I'm sure a lot of people have have at least seen Java and have been asked to install Java on their computers. And Java's favorite sort of famous line is Java runs on 3 billion devices. It's probably more than that now, but I think that was their sort of the quote at the time. So the idea here was Sun was going to go out and write and take this Java virtual machine and make a version for Mac, make a version for Linux, make a version for Windows, make a version for all the different operating systems. And they were going to take responsible for compiling that and sending it out, which is why you have to go install Java. Now, software developers can go write one application in Java and be guaranteed that that application, when it gets compiled to Java, to code that the Java virtual machine can consume, will now run on all these different systems. So it's sort of a hard point to get across, but the big deal here is it went from the developer's responsibility to make sure that all these different operating systems continued to work with their software, and instead abstracted it further. And so that a developer could write software once and then have sort of reliability that as long as the user was using Java and we're using the same version of Java that I developed this code on, I'm pretty confident it's going to work and it's going to work the way I want to. So this was a really big idea. And Sun goes on to be bought by a company called Oracle, who I'm sure some of you are familiar with. And still to this day, Java is one of the largest. I mean, if we go back a bunch of slides, Java is very big. Java continues to be one of the more popular languages, especially for very large companies, just because of its sort of how long it's been around. And it was really the first, one of the first, like, to sort of a paradigm shift of we want to be able to make portable software that we can move from different places and have that confidence that it's going to work as we expected. All right. So closer to today, we're now in 2001. All right, we're heading in the right direction. So at the same time that application developers at Sun were sort of working to make applications more portable, developers and engineers who were working on operating systems were trying to do the same thing. So at the time, the big player in the world was this company called VMware, still around, still a big deal. And they were releasing two different products that allowed us to virtualize at the operating system level. And so they released two of them, type 1, type 2. The difference isn't that important, but I sort of put a diagram here to explain the difference. But most importantly is the idea that in between our actual physical hardware, we insert a new piece of software called the hypervisor that is then capable of sharing that physical software between multiple operating systems. With the important part being that in this diagram, user 1, user 2, user 3, from their perspective, they all appear to have their own operating system running on their own physical hardware, and they would have no idea whether or not they were running in a virtual environment. So this is great. This allowed people who had big servers and big companies to get, once again, more efficient use out of all this physical hardware they had. So rather than sharing it between programs, they can actually have, someone could be running data analysis on one machine, someone could be running the software to power the website on the other. So it really, once again, was sort of the next big leap forward in virtualization, allowing people to get sort of more bang for their buck from their physical hardware. All right. Continuing on forward. All right, 2002. I went on the Wayback Machine and I found what Amazon.com looked like on 2002. So in 2002. So this is a real photo. So if you were an internet user in 2002 and visited Amazon, this is what you would have seen. People liked Amazon. It was great. You could get books. Internally, though, Amazon actually had a problem. And their problem was from how much success they were having. And so I have, the Game of Thrones meme here. Brace yourselves, the Christmas rush is coming. So the problem that Amazon ran into was, once people sort of realized how great it is to order online and have something shipped to your door, they decided, well, of course, I'm going to get my Christmas gifts there. So during sort of the time leading up to Christmas, Amazon had way more use than the rest of the time of the year. So, more users, more orders, more of everything. And in order to support that, they needed to have a whole bunch of physical hardware to support all those users and all those orders. The problem they had was it's not easy to get rid of the hardware once you have it. And so they were paying for electricity, repairs, all the maintenance of this physical hardware and they were paying for the capacity they needed just in December, but they pay that cost year round. So what's the solution to this? Some brilliant person at Amazon said, all right, so outside of the rest of the year, why don't we rent this physical hardware to people? Sort of, thinking back to what we talked about IBM, sort of a similar idea. And thus Amazon Web Services was born. This originally started with just something called S3, Simple Storage Service, where a user could essentially rent hard drive space from Amazon. And then they also rolled out something called EC2, which is called Elastic Compute Cloud for renting virtual machines. So these were sort of two ways that we took this sort of virtualization technology that previously had really only been exposed for sort of really, really big companies using their own hardware, and Amazon turned it into something that anyone could buy and could buy on the cheap. And because it was all virtual, you as the user consumer of this technology, it feels like you have your own computer and it does exactly what you want. You have all the resources you need, but Amazon behind the scenes can actually share that physical hardware and take advantage of that. And maybe the actual physical hardware you're running your web app on is the same one that Amazon is running some of their order processing on. From a user perspective, you don't know this, which is sort of what Amazon realized and was able to, that's why today Amazon Web Services is sort of one of the bigger cloud providers in the world. All right, jumping ahead to more modern time, 2008. President Obama was just elected. We just launched the Large Hadron Collider. Things were going good. And then what else happens? JavaScript takes off. So, way back in time when they were first rolling the internet, people introduced JavaScript and, it was mostly sort of small stuff. Let's maybe, animate this one little icon or maybe have a screen flash to show some animations. But as you can see, as the internet became more and more popular, so did JavaScript in popularity. And by the time we get to 2013 here, JavaScript is sort of the dominant language in the world. And so it runs everywhere on the web. And despite all of its quirks, people sort of embrace it as the primary way to create client-facing web applications. All right, so just 1 year later, the first DevOps conference is held in 2009. It's held in Ghent, Belgium. This is actually a picture I found. It's sort of a cool city. This is some street graffiti that is actually sanctioned by the city and licensed. And then also while I was preparing for this, Ghent actually used to be the second largest city in Europe, way back in the 1300s, 1400s time, very famous for its wool. But more importantly for our talk, the idea, DevOps is a word that's bandied around a lot now, but in 2009, it was it was definitely a novel concept. In 2009, you sort of were either a member of the operations team or you're a member of the development team. And so what that means is operations was responsible for maintaining computers or installing new software, installing security patches, being the one responsible for maintaining databases and making sure that the database lived on a network that the computer running the software was running on too, and so they could talk to each other. That was one job. And you never really knew anything about the software. And then the developer's job was entirely just to write it. And then there was sort of a handoff point. The developer would finish his work, at least wipe his hand, and hand off this sort of package to an operations person to roll that out. And so people got together in Ghent, like I said, and they sort of imagined a world where there wasn't such a split between these sort of two roles. And thus the word DevOps or developer operations was born, with the idea of that for truly successful enterprises, these sort of roles were going to be merged. And so the same people who were going to be responsible for actually writing the application and thinking about the user were going to be the same people responsible for making that application available on the web, making sure that everything worked, and making sure the database was connected. So these sort of got rolled together. And so this was sort of the beginning of the point that people started talking about this role. Problem was, the skill set at this time was very different, and it was sort of a different mindset. Software developers can get very lackadaisical because they know they can get it wrong a bunch of times and keep trying. While the flip side on the operations, one wrong keystroke can take down someone's website. And so it was sort of a different mindset. And so the goal of sort of this conference was sort of start working towards how can we sort of merge these two into something more sustainable for the industry. All right, let's fast forward another 5 years. Pope Francis joins Twitter. And then also in 2013 is the first official release of Docker, and the idea of containers was born. The idea here is that Docker thought that they had come up with this sort of new idea that would solve the problems of our still continue to solve the problems of our current virtualization technology, but with a substantially smaller footprint, and making this a lot easier for a developer to get and work with, and sort of was continuing to push towards this idea of like a DevOps career path. All right. So how does Docker work? So on the left, I have what is sort of a stack that typically represents what sort of virtualization would look like for someone running a machine. So you can sort of imagine this. We talked about EC2, the elastic cloud computing. If I was going to go and rent a machine from Amazon, it would look a lot like the diagram on the left. Amazon has the infrastructure, Amazon has their OS running, Amazon has the virtualization technology, and what I get access to is that guest OS layer. Cool, easy, great, I understand that, that's awesome. But as we can sort of see, where Docker sort of, the big change from the Docker engine is that they sort of realized, why do we need that guest OS? What is that guest OS is providing? So if we think of all the stuff that an operating system does, folders, documents, has a web browser maybe, user input, mouse, maybe a graphics card, all sorts of things, because they're sort of generic. Well, in reality, a lot of applications don't need any of that. If I'm running a website that is handling order processing, that software application doesn't need to be able to access the mouse. It's not how it works. And so Docker sort of said, well, why don't we just cut out that layer? And so our applications can actually get access to just the things they need. So if application 1 was going to be, let's say, a JavaScript application, it only needs JavaScript and the assorted friends. Application 2 is going to be a database. We don't need JavaScript. We just need the database, and so on. So I like this chart because it really shows we cut out a whole stack, and it's just a little simpler to understand here. And so this is sort of how I think Docker picked up because of how simple it was. All right, so let's go to another chart. So yeah, here's another diagram that's just a zoomed in view of what's on the right here. And then with a little better line here. So the word container is tossed around, and so I wanted to highlight when people say a container, what they really mean. So the container here is going to be what is circled here. So it's going to be all the libraries and the binaries needed as well by the application. So app B, like I said, maybe application B is a node library, node software. So that bins and libs is going to include node. It might include some C++ compiler if you have a dependency that needs that. But the point is that that sort of container, you can look at it and I'm only having the code and the software I need to accomplish my task. And so, so you get the advantage of virtualization where you can share the physical hardware and you can take advantage of the fact that you can run a bunch of containers, but it's way more lightweight because each container needs to have a lot less to work appropriately. All right. So this is an example of containers. And then to go back and then talking about DevOps, one of the advantages was it was also super convenient for developers to sort of get their hands in there. So this is an example of a Dockerfile. It's totally okay if some of this looks, you don't quite understand it. I mainly put it here just to illustrate. So each of these are essentially commands that need to get run on a machine in order for an application to run properly. So when I talked about this job of being an operations person, back in the day, let's say your company you're working for, the web app they're running is really successful. They have way more users than they expect, and they needed to go spin up another copy of the software to support more users. Way back in the day, the way this would work is that operation person would somewhere, maybe on a piece of paper, maybe on a Post-it, have these instructions written down. they would go to AWS, they would run to their computer, they would get into the machine, and they would just start typing these commands. And then, hopefully they got them all right. Hopefully they ran them in the right order. Hopefully they all ran successfully. But when they were done writing them all, they can then put the software on there and boom, they were done. Well, so as you can sort of see, that seems a little, might not always work, prone to human error, prone to sort of weird issues where you're like, I know this is working on all the other machines. Why is it not working on this one? Well, it could be the chance that your operations person maybe missed a command. And so it was sort of painful, and it was sort of, like I said, error prone. It was really easy for a human to mess it up. So as we started talking about this idea of DevOps, as a developer, I'm sure some of you are familiar with GitHub. All the work I do is always saved. There's always a version of it, and I always can go back to the working thing. And I never can essentially lose my work. I don't have code written down on a Post-it. I don't have it written down on a text file. It's permanent. So, sort of the developer part of that DevOps said, all right, well, let's do the same thing with these sort of instructions that we need to run. And so this is where the Dockerfile sort of got born. So at the end, all Docker is we're going to run this file to create one of these containers by grabbing, so I've mentioned JavaScript a lot. So let's say application B is a JavaScript application. Essentially, this Dockerfile is just a set of commands that the Docker engine executes as part of creating the container. So it was very reusable. You could run them again and again and again, and the Docker engine is always going to run the right commands in the right order. And more importantly, I can take this file and I can put it in a place like GitHub. So when my current operations person maybe leaves for a new job, and someone else can come in and they don't really have to hope to find that person's notes. It's recorded somewhere permanent with versioning on it. So great. So this is really cool. And then I think to highlight the other advantage here is that, as we mentioned in this slide, we've cut out a huge portion of this chart on the left of the guest OS. And in terms of like pure space that takes up, that's a lot. I don't know if anyone has either like installed Windows recently, but we're talking about several gigabytes of data that have to be kept to run a Windows, to run Linux, to run a Mac. So the advantage here is that these containers that we're going to be built here are much, much smaller, which gives us the advantage of that these can then be shared. And so that first line, it says from node 13-alpine. So that's a little confusing, but essentially what happens is the person who maintains JavaScript can go out and make a really bare bones JavaScript container, do all the installs they need, install Node, install the C++ compiler, maybe there's a couple other things, and then make that publicly available. So for anyone who says, all right, I'd like to run a Node application, all they need to do is reference it from node 13, run their sort of, their bread and butter, their custom instructions, and they're good to go. And then they don't need to worry about ever having to figure out how to install Node themselves. So by removing this guest OS, we were able to then make these containers small enough that they become shared on public repositories. And there's something called Docker Hub, where you can see a wide variety of containers for doing pretty much anything you want. And then this example here this is sort of how easy it is. If I want to run MySQL, which is a database, all I have to say is Docker pull MySQL. It's going to go out into the web. It's going to go to this public repository. It's going to pull that container and pull it down, and then I can run MySQL locally. And so it's very convenient for developers. This was a command I just actually ran this morning on my computer. I think it took 2 minutes. And then just for reference, 2 minutes to be able to run MySQL, if you compare that to like 10 years ago, we're talking about 2 hours. Hopefully it works. So as you can sort of say, this is like a huge advantage for local development is developers can share sort of essentially fully working stacks of code that can then be run anywhere. All right, so this is great. And then sort of coming to the end here, this is really good for small companies actually. And it's really great that this technology is here because it allows companies like Amazon to get in the game. And so, like I said, Amazon originally offered something called elastic cloud computing, which is, was a great, but and it solved a lot of problems, and it made it a lot easier for smaller companies to sort of get more guaranteed billing and how much things are going to cost to run their application. It still came with the downside of, like I said, the elastic cloud computing, you're getting the operating system, and therefore you are paying for the operating system. And so when we're looking at here, Amazon took the same technology and then just exposed it in the same way that they exposed individual operating systems. Amazon makes an offering called the Elastic Container Service, which allows you to run these Docker containers, but using the smallest footprint you need to accomplish your goal. So it goes a long way. It makes it a lot cheaper because you are really just paying for what you need. And then it makes our life a lot simpler because this same command of pulling MySQL works just as well as Amazon to pull your software in. And so it makes the maintenance much more flexible for developers to get it right. So this is sort of where we are today. I think you'll continue to see containers continue to be a buzzword just because of the flexibility and the confidence they give for developers that they've gotten their application correct. And then as Amazon continues to expose more of this, it becomes a cost-saving advantage for companies to use containers over using something like an operating system. Because of the portability of, if you don't want to work with Amazon anymore, there's other cloud providers that also provide, Docker engine and the ability to launch your own containers. So it allows you to sort of get the advantage of best bang for your buck and increasing the portability. And that's sort of where we are today. So I will take the time to open it to any questions or thoughts or comments. Let's take the next sort of 5 minutes or so. But yeah. And let me know if anyone would like to see any other slides. I'm happy to go back. My favorite language to use, it's probably TypeScript, which is, if you haven't heard it, it's a superset of JavaScript. I've come typically from a sort of typed system, and it's sort of the best of both worlds. All right, a couple questions here. How can we learn more about Docker? So I think that the easiest way to honestly learn about Docker is install it locally. If you have a computer that you're doing any sort of software development on, there's a lot of great tutorials, and you can just sort of pull down the software and run it locally. I think the beauty of Docker is like sort of that high level overview. As a software developer, that's pretty much all you need to know in order to take advantage of Docker. There's a lot more to know about sort of the nitty gritty of how the computer architecture works. And sort of, there's definitely plenty of online classes on computer architecture from Coursera and Udacity if you're interested in more of the actual, ones and zeros for how Docker works. But in terms of using it as a software developer, I sort of think this is a great overview and gives you the option gives you the option to go and start just playing around with yourself by just installing Docker from the website. All right. Do you like TypeScript because it allows for front end and back end? I mean, that's part of it. I like it because it provides the flexibility. And so we talked about Java. Java is a typed language, meaning if I'm going to say that I have a variable, I have to tell Java if it's going to be a string or a number. TypeScript gives me the advantage of I can ask if it's going to be a string or another number, but I don't have to tell TypeScript. I can let it figure it. I don't have to tell TypeScript if I'm not sure yet. So it gives you the flexibility of hardening your code by adding in a type system, but at the same time gives you the sort of the speed to quickly prototype and make changes. What's the most unique use of Docker images that you've seen? So the most unique use, so I do some work with a civic organization, and then I was working with someone who is not particularly technical, and we were having to run a whole bunch of scripts over and over again and process some data. And so rather than having to go out and maybe go install Python on their device and making sure that we all have the right Python dependencies, I quickly showed them how to install and one-click run a Docker image. And so sort of this non-technical person was able to sort of take my work and then run it without having any additional setup or any additional dependencies. How can it be used for object-oriented programming like Java? So Docker is agnostic of the language. I referenced Node a bunch, but if we go back a couple slides, for that first line from Node 13 Alpine, if you're going to do something, if you wanted to use it for Java, that first line becomes from Java version, I forgot, the versions have gone crazy, version 13 or whatever. So it ends up working the same way. And then that line on line 17, command node server.js becomes command node, command Java C, my main.java. I'm sorry, I haven't done Java in a while. But the important part is it's agnostic. If you want to run Java, if you want to run Visual Basic, if you want to run Objective-C, Docker doesn't really care. And it just, as long as you have the sort of necessary dependencies to run those. So it's less verbose compared to another language like Java. So I think about this TypeScript. Yes, so it is less, it's much less verbose than Java. While still, if you want it to be, giving you the same level of type safety that Java does. So yeah, you can write it in a much less verbose way. And if you know Java, TypeScript is sort of is not that much of a leap, and I think a lot of people will sort of like how it feels. How does a Docker container work with something like Kubernetes? Heard of it, not sure the use case. Yeah, that's a great question. So because we're always sort of like building upon abstraction. So we talked about the fact that, all right, so let's go to this screen. My software that I'm writing, it's great. It needs to run a MySQL database in order to operate. Turns out it's super successful. And so I need to run multiple MySQL databases, and I need them all to connect to the software. And so we're going to run MySQL in cluster mode. Things sort of get complicated there. And then so Kubernetes solves a lot of solutions, but sort of one area that Kubernetes solves is it lets you sort of abstract away how many containers you're running into the more idea that there's a MySQL service. It exposes you a way to query the database, but you don't know if it's one big MySQL container, if it's a bunch of MySQL containers. So that's some of the solutions that Kubernetes solves. And most importantly, let's say we had this idea of a MySQL service, and overnight, oh no, my pager goes off, the site's down because we've had so many people hitting the site. Kubernetes can actually, you can configure it such that it will automatically increase the number of containers you're running to give your site more bandwidth to support more users. But yeah, so Kubernetes, it's a little bit more technical, and there are more, unlike sort of containers, Kubernetes is one solution to what they call container orchestration. And there are other, Docker has one called Docker Swarm. There are other solutions to this problem. But good question. Can you briefly explain the relation between AWS and Docker? Yeah, so they are, not at all related in the sense, they're separate companies, they do their own thing. Docker is solely focused on sort of the Docker engine and making that work great for local developers and maintaining, like I said, that public repository of useful containers like MySQL and Java images. And then AWS is sort of, So yeah, that's what they're responsible. But at the core of all of it, sort of Docker is one of the maintainers of sort of what they call a specification for how containers should work. Amazon goes out and then implements that specification. So that same image you wrote to run on your local Docker image work on your local Docker engine then also works on AWS. So like a lot of these big sort of software companies, there's a lot of sort of, among the developers, synergy, sort of working together, but they exist as separate companies. And so Docker was around a lot longer than Amazon was offering containerized solutions. And then, like I said, Amazon does a lot more than just containerized solutions. We're talking about, storage, domain names, lots of more stuff than just what Docker is sort of much more tightly scoped to. Which is better for auto scaling an application containerized with Docker, Docker Swarm or Kubernetes? So I think people hate when they get this answer, but neither. It's a lot of these sort of decisions we're making on sort of the architecture is going to be very context specific. So it's going to be depending on what you're doing, where you might be running this software. For example, Kubernetes is a Google supported project. It has the Google Cloud might, this is all a little off the cuff because I haven't actually used Google's cloud that much, but might have better UI for working Kubernetes. Or you might look at Kubernetes and the syntax for the files descriptions might be confusing you, but you might look at something like Docker Swarm and it looks a lot better. And so, at least for me, the heuristic I try to use is always about usage and what sort of you've seen real companies use live in the world, and not just sort of maybe articles on Medium of someone doing a hello world. Great, really good questions. Yeah, so anyone else? Happy to keep answering if there's more. And yeah, these slides I will share. And then I will also try to include some maybe other resources for learning more about Docker and getting started. But yeah, thank you all for attending my talk. Really good questions. I really appreciate everyone listening and going through everything.